Okay, let me start. So after all this very heavy physics, let's have a little bit of relaxation with some mathematics that is going to be of use to us. So let me just remind you all that if you have a function f of z that is holomorphic in the complex plane, then we all know that the function f of z is equal to 1 by 2 pi I. If this is the point z that I have, and I choose a closed contour like this, 1 by 2 pi I, closed contour like so, f of z prime dz prime divided by z prime minus z. Okay? So this is one version of Cauchy's theorem that is going to be of interest to us. Cauchy, C-A-U-C-H-Y, not Cauchy, but Cauchy. This is Cauchy's theorem, like so. Okay, so so this is the kind of version of Cauchy's theorem that we are all accustomed to, but I want to massage this a little bit and bring it into a form that is suitable for us. This is a very nice function which is got nice properties everywhere in the complex plane. But our functions are not so nice because we already saw that in some cases that in our T-plane, in our complex T-plane, we are likely to have a branch cut starting at some place at 4m pi squared like so, okay, 4m pi squared. But doesn't matter if I choose a contour like this is perfectly okay because I don't cross the branch cut anywhere, so I'm doing this fine. Okay, so what I'm going to do is I'm going to run a movie for you and then deform this contour a little bit and see what happens to the function as I deform the contour. So let us say that this is some point over here, and this is the original contour that I started out with, and then I have to, of course, always surround this contour. So if I have a contour like this, it is still fine, no problem. Now let me deform this a little bit more and do this and come back around, no problem. My function is still well defined. But then let me start trying to make this more interesting because we said that all our physical measurements are going to be right on the branch point. In fact, most of the time, it's going to be the value of the function coming from above. Okay, so let's do that, and let me choose a nice contour that embraces this branch cut like so, and then does this, and goes all the way around, and then it does this, and then it does this, and then it comes back around. Okay, so this is fine. You will agree that whether it was a function like this or a function if I have a branch cut over here, whether it was this or whether it was a contour like this or eventually a contour like this is all fine, and that my Cauchy's theorem is going to work fine as far as we are concerned. Okay? But now there's something that I want to do, which is an integral on a closed contour like this. I want to replace it by a real integral over here. And how do I do that? I have defined my contour in such a way so that it has a height that we call delta over here and a height delta over here. And then I want to argue that the contribution from this large circle is going to, so I also need the sense properly, no? I need to have the sense properly. So it's counterclockwise like this, counterclockwise like this, okay? So while we are having all this fun, now you have to tell me eventually how do I turn this into an integral that is going to be an integral over here and an integral over here, and what's going to happen to this particular function, okay, as we do this. Okay. What are the various steps that I need in order to make this a nice integral along the real energy from 4m pi squared to infinity? I want to have a version of this integral. Okay. So there are certain circumstances under which the contribution from this large circle are going to be 0. And let us just for the moment assume that this is the case, that the contribution from here, contribution from the large circle, contribution from the large circle goes to 0. So the only thing that will be left will be the integral along this in the positive direction from 4m pi squared to infinity, and a corresponding contribution from infinity to 4m squared in the negative direction, okay? And the value of the function over here, is going to be real f of t plus I times imaginary part f of t over here. Now I'm going to ask you to guess what is going to be the value of the function over here below the cut. I'm going to ask you to guess what is going to be the function over here below the cut. And if so, why do you think that that should be the case? Okay. Somebody tell me. So my integral now is going to be an integral from R plus an integral on this path. Let me call this A and let me call this B. An integral along A minus an integral along B over here. And I'm going to argue that this is going to be equal to 0. And because the form factor from physical reasons is expected to go to 0 fast enough up to something known as a subtraction, which I will introduce a little later. For the moment, you just accept that it is going to go to 0 even if I don't perform the subtraction. So that also gives me an opportunity to introduce the notion of a subtraction, okay? And this is a rigorous theorem for form factors which goes under the name of Kanazawa-Sugawara theorem. That this is so that it goes, that this contribution goes to 0 irrespective of which direction you evaluate this function. Now you may wonder, oh, it's going to 0 in this direction, but does it also go to 0 in that direction, etc. It goes to 0 irrespective of this. So now the question is, what is the integral from here and what is the integral from here? Okay. Now I'm telling you that the function here is real part of f of t plus I times imaginary part of f of t. Okay. Now what do you think is going to be? Do you think it will be real f of t plus I plus imaginary times f of t? Do you think it will be the same above and below? If it's the same above and below, then in the limit that delta goes to 0, the integrals will also become the same with a minus sign, so the integrals will cancel each other. So that is unlikely to be the case. So what do you think would happen? Yes, and it's a very important principle in complex variable theory, and this is known as the Schwarz reflection principle. So here the value of the function will be real f of t minus I imaginary part of f of t. Okay, so you will get the answer to be actually twice the integral from A. This is a very beautiful result, and the reason why this is so is that such functions where the value f at z star is equal to f star at z is a class of functions that are known as real analytic functions. And in many of the cases that we Yeah. I haven't even said what it is. I'm merely saying that it's the integral coming from A, and this is minus the integral coming from B. I haven't said what the integral is. I'm merely saying that it's a sum of various contributions, one from here, one from here, one from here. Okay, that's all that I'm trying to say. And correctly, I have not yet said what it is. But in order to say that it's the imaginary part, we have to introduce this notion of real analytic functions, and all these form factors and many of the objects that we come across in particle physics, except in the cases of unstable particles. As my friend who asked about omega, the omega form factor is not in the same thing, is not in the same category because it's actually unstable. So the corresponding form factor is not of the real analytic type, but that's so, okay? So these things are real analytic functions where f of z star is f star of z, okay? So having said this, then our entire integral now is the difference between these two where the real parts cancel out. No, actually, this is not correct. I should keep it as it is. Yeah, you're right, the imaginary part. Or I should put twice the imaginary part coming from A. Thanks. Tuhin was correct, twice the imaginary part coming from A. So the entire integral now will be such that f of t is equal to 1 by pi. The 2 is gone, times not only imaginary, 2i times imaginary part divided by 2 pi I, 1 by 2 pi I, 2 pi I, open and close these brackets like so. So this is equal to imaginary part of f of t prime divided by t prime minus t prime, okay? Now let me address that issue of subtraction. This is a very good opportunity for me to be able to address the issue of the subtraction. Now supposing this contribution did not go to 0, yeah. For the moment, yes, yeah, 4m squared to infinity. So supposing it didn't, let us say that this is true. 1 by pi integral 4 m pi squared to infinity, imaginary part of f of t prime. Never mind my uppercase and lowercase. What I'm going to do is I'm simply going to add and subtract term to this, assuming that, see, we physicists don't mind adding and subtracting divergent quantities to get perfectly sensible answers. It would, of course, break Dirac's heart, but he's not here anymore, so we don't worry about him. 1 by t prime like so. Okay, so let us now regroup these terms and write this as 1 by pi integral 4 m pi squared, imaginary part of f of t prime by t prime dt prime, plus note what we get over here. We get a t by t pi integral 4m squared to infinity, imaginary part of f of t prime. Now note this, t prime minus t dt prime. So if you thought that this integral over here on the large circle doesn't converge fast enough, what you can do is you can divide it by an additional power of t prime over here so that it damps out faster on the large circle. And the price that you have paid for it is the introduction of a new quantity that you have to somehow fix from some other source. And this is what is known as, so this, if you look at this, starting out with the parent expression, you will notice that this is nothing but f at 0, okay? F at 0 plus this term over here. So this object here is an example of what is called a subtraction constant. So this is a subtraction constant. Now one of you has to help me generalize this further. Supposing this still doesn't converge, then what do you think we should do? Supposing this still doesn't converge, what do you think you should do? Let us do this process one more time. Then you have to take f of 0 plus f prime at 0, multiply it by t, plus, this time it will not be t, but it will be t squared by pi, and an integral from 4m squared to infinity, imaginary part of f of t prime. Now tell me, what should it be over here to make this thing better behaved, to make it better behaved? Of course, the Cauchy kernel is still here. T prime minus t is still there. T prime squared, okay? So this process can go on endlessly until you get convergence, okay? But each time you do a subtraction, that means that this has to be fixed from some source. This also has to be fixed from some source. And each of these, so this time this is an example of two subtraction constants. Two subtraction constants. So what do you think is going to tell you whether you can stop at one subtraction constant or two or three and so on? So let me ask you a question. What is going to tell you or give you a hint when you can stop and say, look, this Cauchy integral will converge and I can stop here? There has to be something which tells you that asymptotically things cannot grow faster than something, okay? If you have a bound on some physical quantity that is given from general principles and the bound is shown to be true and rigorous, then you can say that I'm going to stop with one subtraction, stop with two subtraction, stop with 33 subtraction, whatever. But provided such an upper bound exists. Any idea about what kinds of bounds exist on some physical quantity? One of you has to answer. This is about form factors, but if I asked you about cross sections, what would be your answer? Actually, you know, in life, it's scattering which is the real experiment that you carry out. And when you do scattering, then what do you measure? In scattering experiments, what do we measure? Cross sections. It could be differential cross sections, or an elastic cross section, or the sum of the elastic and inelastic cross sections, which is the total cross section, okay? Now, do you think that there is some bound on cross sections? And if so, why? And from what principles can you get such a bound? Unitarity is a reasonable answer, yeah. So we will get some bounds now from axiomatic field theory. It says that cross sections cannot grow faster than something. If it is a total cross section, what is the only variable that you have for a total cross section? It's only S. It's only the center of mass energy, right? If it's differential cross section, of course you have two observables, but if it's a total cross section, you have only one variable, which is the square of the center of mass energy, okay? It's a very generic theorem based on complex analysis, but applied to form factors. It's not some theorem in complex analysis, it's a theorem for form factors. This is dates to about 1965 or so. It's very, I don't know the exact, I can look into my life-saving bag and then give you the appropriate medicines, you know, and you can have a look. It's very nicely discussed in the book of Euler. Yeah. Okay. So, returning to my question, there is a fundamental result in field theory which tells you that cross sections cannot grow faster than the logarithm of the center of mass energy, and that is known as the Froissart bound. It's an extremely important result, and this Froissart bound actually has implications even for things like form factors. And if you wrote dispersion relations of this kind for scattering amplitudes, the Froissart bound will fix for you the number of subtractions that are needed, okay? Now, this is a very simple dispersion relation because for a form factor, there's only one variable. A cross section is already more complicated. It has two variables. So the corresponding dispersion relations that you have to write are obviously going to be more complicated. So you may say, in that case, let me fix one of the variables and write a dispersion relation for my cross section in the other variable. Keep one of them fixed and vary the other. And in fact, that is what is done. Those are called the fixed T dispersion relations. These things are done. Okay. So I should say, what is the Schwarz reflection principle? So here, the imaginary part of f of t we saw over here is 1 by 2i times f at t plus I delta minus f at t minus I delta. So the Schwarz reflection principle says, that in the complex plane of any function over here, if there is a domain where the function is real, if there is a domain of analyticity includes a segment of the real line of R, where the function is real, then it must be of the real analytic type. Since Arun asked me this question, all these complex variable theory people, they have at their fingertips other very important results of complex variable theory. And let me just mention one of them, maximum modulus principle. And even the Fragment-Lindelof theorem, which I never thought has any possible application in physics, but it does, Fragment-Lindelof. All these theorems are used, and please note that everything that we have talked about so far is functions of a single variable, single complex variable. Everything so far is function of a single complex variable. Okay. So returning to my other example, which is that of the electromagnetic form factor of the pion, which is what we were talking about, electromagnetic form factor of the pion. I'm told that the mistake that I made was S is 1 plus IT in the book of Martin and Spearman, which I request you to check for yourselves. So what we are interested in is the imaginary part of this process of photon blob like this producing a pi, okay? And we said that on the right-hand side, the imaginary part is on the left-hand side, and on the right-hand side is the sum of TT dagger, and this is, again, something like this, rescattering like this, pi, like this. Okay. So what we see over here is, even in this imaginary part of the electromagnetic form factor, on the right-hand side, because it's t squared, you will see the appearance of the pi scattering amplitude. So the statement over here is that the imaginary part of f of t will go as t star pi of t f of t in the elastic region. And to answer the question my friend asked, there are obviously other diagrams also as the center of mass energy increases. So you may have something like production of 4 pions like this, if the energy is high enough. So 4 pion intermediate state. You can also have kk bar intermediate state like this, pi. All these are allowed provided your energy is high enough. But in the region 4m squared less than or equal to t less than or equal to 16m squared, only 2 pion intermediate state is allowed. okay? So, instead of, of the form factor, of the form factor. Of this, it's a 3-point function. No, but on the right-hand side, you see part of the scattering amplitude appearing. So that's what I want to demonstrate over here. Okay. Yeah. Elastic region is no other particles allowed except the 2 pi. It's elastic of the scattering process. 2 pions to 2 pions, that's the elastic region of the pi scattering amplitude, not of the form factor. Okay. So the T here, which is this here, is the elastic region of the scattering amplitude. So the best way to deal with this is to give an example. Okay. And the example, again, comes from chiral perturbation theory, which is the most useful way of looking at this at one loop. Okay. So this example is taken from the book of Donahue, Golovich, and Holstein on dynamics of the standard model. It's a very good book, which also explains in great detail all these otherwise pretty complicated calculations. Okay. So those of you who want to study about chiral business, it's one of the best sources to study because it actually does all the calculations. So I hope I have the page. I have the page somewhere. I don't know where I have it though. Here it is. Okay, so their symbol again is different. Okay, so here it is, electromagnetic form factor at one loop. Electromagnetic form factor at one loop. So this is from Donahue, Golovich, Holstein, second edition, page 217. So there are two diagrams at this order which contribute to the pi scattering amplitude. All these are pions. There's one like this, and then there's one like this. And I don't have to explain these because it'll be covered in other courses. And this result is, and this is shown as a function of q squared. By now we all know what is q squared. So there's a 1 plus 2 times one of the low energy constants, L9 of this second order Lagrangian. So this is one of the low energy coupling constants, but that's not what is of interest to us. What is of interest to us is this thing here, 1 by 96 pi squared f pi squared times. I was told that many of you will be doing these problems in the evening session. So this is a problem where you can actually check that this is indeed the case, that it respects that version of unitarity given over here, over there, minus q squared logarithm of m pi squared by mu squared plus minus q squared by 3. Okay, like so. What is this h of q squared by m pi squared? It's again the same one loop integral that we did from Ramon's book. Okay, so this h of a again is defined by them in the following way: minus integral 0 to 1 logarithm of 1 minus ax times 1 minus x dx, like so. Okay. Now I'm supposed to see and check that the imaginary part that is generated by that thing over there is going to have a structure like this, that it is supposed to have a part that looks like the pi scattering amplitude that is multiplying f of t. The pi scattering amplitude over here with the appropriate quantum numbers, pi scattering amplitude with the appropriate quantum numbers. So that is what I need to show over there. Not even the pi scattering amplitude, but the correct partial wave. It's supposed to have the correct partial wave, which brings me to the next notion and idea. What is a partial wave? Okay. How many here know what is a partial wave? You may have done it in your quantum mechanics course as well, not the, I certainly hope the teachers know, but I'm asking about the students. Okay. Okay, so this gives me an opportunity to introduce the next set of ideas, which has to do with pi scattering, the amplitudes, and the partial waves. Okay. So in order for me to actually discuss a simple example of this kind, I have to describe the more complicated things, which has to do with the amplitude, which has to do with the partial wave projections of the amplitude onto those partial waves. So let's do that. Okay. How many of you here are aware of pi scattering? What is pi scattering and how do we define it? Okay. So that's the question that we come to next. Okay. So here I need the correct partial wave. What's the partial wave that I need? Remember that we have photon, which is going to have vector meson dominance rho, which then gives pi plus pi minus like so. So photon is a JP equals, somebody, JP, 1 minus like so. So I need to find the partial wave corresponding to L equals 1 partial wave, L equals 1 partial wave of pi scattering, of pi scattering. So that is what has to be done next. So now we will have a bunch of definitions, not so difficult. So if you just kind of come for the ride with me, I feel like an Indigo steward telling you all to enjoy the flight. Okay, and at least I don't have to tell you all how to use the life jackets. Okay, so yeah. Q squared. It's the momentum carried by, very good. I think it's the Q squared is over here. No, I think it's carried by the photon here, Q squared. Yeah. It's a photon moment. Yeah. This one? It's one of the low energy constants that is introduced to absorb the divergences. Okay, so this brings me, sorry. I thought it's all part of the chiral perturbation theory. So this is the pion decay constant. Pion decay constant. So L2, which I hope Anish has introduced, or maybe he's doing it tomorrow, will be d mu u, and this u here is going to have exponential of I lambda a pi a divided by f pi, like this. So this is the pion decay constant, which shows up in the chiral Lagrangian because it's a Goldstone boson, and then the pion decays into a lepton pair. So it's measured, the strength of that is measured by the pion decay constant. Yes, it's the external field technique that was invented by Gusser and Leutwiler in their discussion of these things. So you can introduce not just the electromagnetic field, but weak fields can also be introduced. Yeah. Yes, yes, yes. Yeah. No, this is a leading order that comes from L4. Yeah, that comes from L4. Again, the notation of Golovich and company is different. Okay, that is why they have a 2 here. Yeah. Okay, so now this brings me to pi scattering, and I will introduce simple examples so that we don't get blown away by this. So this is the scattering of 2 pions, and as you know, pions lie in an isospin triplet. Pions lie in an isospin triplet. In contrast to proton and neutron, which lie in an isospin doublet. Everybody knows this, right? So this is SU2, you can have pi 0, pi plus, pi minus, k's, all the k's, k naught plus, etc. I've forgotten, and the eta like this, okay? So this is the JP equals 0 minus part of the spectrum that you can introduce this. So let me have a general pi-pi scattering where each of them will carry an isospin index pi alpha with momentum p1 and pi beta with momentum p2, scattering into pi gamma with momentum p3 and a pi delta with momentum p4. Okay. So the so-called S channel is associated with pi alpha p1 plus pi beta p2 scattering into, so these are now the incoming particles, pi gamma beta p3 plus pi delta p4. Whereas, so this is the S channel, so the T channel comes from crossing these particles, and then you get pi alpha p1 plus pi gamma with minus p3. So here I should have some arrows, arrow in, arrow in, arrow out, arrow out. Different books have different conventions. Please keep that in note. Pi beta minus p2 plus pi delta p4. And then finally the U channel. Somebody tell me what's the U channel? Pi alpha p1. I took this to the other side, no? And I put pi gamma to the side. Now I should bring the pi delta to the side. Pi delta p4, pi beta p2 plus pi gamma p3. And the invariants, of course, are S equals minus p1 plus p2 squared, which from momentum conservation minus p3 plus p4 squared, T is minus of p1 minus p3 squared minus of p2 minus p4 squared. U is minus of p1 minus p4 squared minus of p2 minus p3 squared. And I ask you, what is S plus T plus U? In this case, these are the Mandelstam invariants, S plus T plus U. Sum of the squares of the masses, in this case, they're all the same. So it's obviously all 4m pi squared. 4m squared. It's also good to have the scattering angle in the center of mass frame, which is for the S channel, T is equal to minus qs squared 1 minus cosine of theta s. Let's see. You often have to remember that in the S channel, cosine theta is T minus U by 4 minus 4 m pi squared minus S, okay, or sorry, S minus 4 m pi squared. So please remember that these are not just arbitrary symbols, but these symbols also represent specific characteristics of a given scattering configuration, that this cosine theta is given by T minus U by S minus 4 m pi squared. And the physical region is, physical region in the S channel, physical region is S is greater than or equal to 4. Why? Unless you actually have enough energy. I mean, even if the momentum is 0 between the two particles, you have m squared plus m squared, which m plus m whole squared is 4m squared, right? So S is greater than 4, and T is less than or equal to 0, and U is less than or equal to 0. This is all just kinematics so far. I have not even introduced the scattering amplitude. So that's a crucial thing. We have to introduce the scattering amplitude. So you see these things here are isospin triplets. Okay? The strong interactions conserve isospin. Strong interactions conserve isospin. So I ask you, if it is isospin triplet, then each one of them here lies in a three-dimensional representation of SU2, right? Three-dimensional representation of SU2. Now, if you take 3 cross 3, what can you get? 3 cross 3, or if you take, or let's think of them as spins. Instead of isospin, the same algebra is for spin, right? Two spin 1 particles. What are the possibilities for the total spin? You have two spin 1 particles. What are the possibilities for total spin? Come, quantum mechanics, all of us have done it. Total spin possible? Yeah, which in this case is? Yeah. Exactly. So we have 3 isospin amplitudes. Exactly. So we will have 3 isospin amplitudes in the S channel. And this transition matrix element for phi alpha P1, phi beta P2, S, phi gamma P3, phi delta P4 is given by various possibilities of isospin conservation, delta alpha beta, delta gamma delta, and I'll call this ASTU. What are the other possibilities of having various tensors stitched out of these isospin labels? You can have a delta alpha gamma and delta, beta delta, and I now have to switch it because now it's going to involve P1 and P3. So this I'll call ATUS. And then finally a delta, alpha delta, delta, beta gamma, and I'll call this A of UST. And here I've used a certain property which is known as crossing, that it is the same function ASTU that shows up whether it is in the S channel, the T channel, or in the U channel, okay? So this, in each one of these sentences that you see in these standard books, there's a lot of effort that has gone into being able to distill it and express everything in just one sentence, okay? So this is the most general matrix element for this scattering matrix element. Okay, so this is fairly useless because in real life we have scattering where isospin is actually conserved and you have so-called amplitudes of definite isospin, and as my friend up there told me, there should be T0, T1, and T2, and they are all in the S channel, so I'll write it like this: STU, STU, and STU. And I'm going to give you a result, and you have to believe me that it's true. Not only do you have to believe me that it's true, but I actually own Mathematica programs, which I wrote myself, which has checked every piece of algebra. And if you people are nice to me and you deposit money in my PayPal account, then I may give you a copy of the Mathematica notebook. That bad joke was just to make sure some of you are awake, right? Right, Devajyoti is there. He's finally managed to get a smile out of it. Okay, so this is 3 times ASTU plus AUST plus ATUS. Very nice. But I should also tell you that each of these is invariant under the exchange of the last 2 labels. Okay, so this is symmetric. ASTU is ASUT. Okay. This is a property that is satisfied by this. So this is A TUS minus A UST, and finally this is A STU plus, no, there are two independent variables, S and T. U is fixed by the conservation law that ST and U are 4m is equal to 4m squared, okay? Only two independent variables. What this means is that A is a function of the square of the center of mass energy and of the scattering angle. T is related to the scattering angle. How is it related to the scattering angle? Yeah, cosine theta ST minus U by S minus 4m squared, okay? U is not independent. You can put S back here. So this is at a particular center of mass energy. So the scattering angle is related to both the center of mass energy as well as a momentum transfer. T is related to the square of the center of mass, is related to the square of the momentum transfer in the center of mass. Okay, that is what is T, physically speaking. That is why it is also related to the scattering angle. This is A TUS plus A UST. Yeah. Okay, so when you write ASTU, it is evaluated when the object in the first place is a center of mass energy, okay, for a given scattering process. Now, so that's the position of the first variable. Numerically, here it is the same, whereas when you come to this line over here, for that configuration, you know what is T, but you plug it into the first place, which is the center of mass energy. I know it's a little complicated, but that's how it is. No. Sorry, I don't know how to explain this any better than this. But again, these things are necessary for us to establish the various properties of pi scattering amplitudes. Let me also tell you how we get these funny factors of 3, 1, 1. These come from coupling the isospin triplet to the isospin triplet to the final state with these three definite isospins in the final state, okay? And the matrix element that couples these is the Wigner 9J symbol for this SU2 algebra. You can do it correspondingly, let us say, for pi n scattering, where n is in a doublet and pions are in a triplet, okay? So there are corresponding Wigner 9J symbols which will give you this answer also, okay? So then the 9J symbols are then related to the 6J symbols, which you can explicitly evaluate and get these objects, okay? Now, after this complicated thing, let's do a simple example. Let's do a simple example, which is related to what Tuhin was asking about f pi squared. Let me tell you that at lowest order in chiral perturbation theory, lowest order in chiral perturbation theory, and this was given by Weinberg based on current algebra, because at that time there was no chiral perturbation theory. But he used phenomenological Lagrangians to generate current algebra. So he gave, at the lowest order, what is ASTU. ASTU, he said, and this is a very remarkable thing, is a very simple linear function, S minus m squared by, I don't remember it's f or f squared. I think it must be f squared. F squared, thanks. ASTU can't possibly be simpler than this, okay? Now I ask you to help me evaluate T0, T1, and T2 so that before we are done for today, I can finish my electromagnetic form factor. Somebody please help me. Oh, I should do it in the same order. Yes, T0, T1, T2. Somebody help me with this. Can I ask one of the students to come and do it? No. How about you? All of you are so shy. I guess I have to do it myself, okay? So 3ASTU is 3s minus 3m squared I'll put an 1 by f squared outside, okay. Then AUST plus U minus m squared. Then ATUS is plus T minus m squared. Now tell me, what is this? Three S plus T plus U minus 5m squared divided by f squared, okay. Now S plus T plus U is 4, plus 4 minus 5, minus 1, 2s minus m squared by f squared, okay. Now let's do this. This is U plus T divided by f squared, so that is equal to 4 minus s by f squared. How about this? Somebody has to do this. I'm getting tired, I'm not going to do this. TUS minus UST, somebody? Devajyoti has to help me with this. Tell me. T minus m squared minus U minus m squared, what does that give me? T minus U, that's all, nothing more. T minus U. T minus U. Now comes the next question. These are the amplitudes. What did we say we needed? We said we don't need just the amplitudes, but we need something else. Something else. We needed partial waves, right? Now we have to take each of these amplitudes and project them onto partial waves. How do we project something onto partial waves? Somebody has to remind me what is meant by a partial wave. Partial wave of any amplitude is an expansion in terms of, you heard me, right? You heard me. Partial wave is an expansion in terms of Legendre polynomials. Of what? Polynomial in what? Legendre polynomial in something, no? What's the argument of the Legendre polynomial? Come on, folks, you've done it in your Jackson, no? PL of something. PL of cosine theta, right? When you see a cosine theta there somewhere, T minus U by S minus 4m squared. All of you have seen partial waves. So, each of these Ti of STU can be expanded in partial waves, sigma. How many partial waves are there for each? Infinite number of partial waves which carry definite angular momentum. What label shall we use for angular momentum? L, okay. How about L? PL of what? Cosine theta. Some other factor here? 2L plus 1, right? Now here it has an S, a T and a U. So far it has only a cosine theta. What happened to the S dependence? The S dependence produces what is known as the partial wave amplitude, FIL of S. So this is the partial wave amplitude for each one of these isospin amplitudes, okay? And we should know that Legendre polynomials are normalized by this dz from minus 1 to 1 by 2L plus 1 by 2, I think, like this, is equal to 1. Do some of you remember what some of these Legendre polynomials are? P0 of 1 is 1. P1 of z is z. P2 of z, 3z squared minus 1. I think some other factors there. By 2, etc. Okay. Fine. So, but this is very nice because if you didn't have this orthogonality property, you would not be able to produce the partial wave from the amplitude. Now you can get each one of these partial waves by projecting it onto a given partial wave by using the orthogonality property. Otherwise, you can't do it, right? It's absolutely essential in order to do this. There's one more thing that I want you to do. I want you to identify this thing and tell me what this is. Where is my friend over here? Okay, it's not here. I have to go back to finish that exercise. But before that, let me introduce one more notion over here. So what can you say about this FL of S? FL of S is also again going to be a complex function. And where will it start producing an imaginary part? Start producing an imaginary part only in the physical region above S equals 4m pi squared. So in general, it'll have a real part and it'll have an imaginary part. A real part and an imaginary part. And a real part at this thing over here has a very useful expansion, which is given by, I think I have misplaced that definition, for S greater than or equal to 4 will be q to the power of 2l, where q squared is equal to s minus 4m squared by 4. Okay. So this is again a useful combination. So it's q to the power of 2l times definite isospin I times a il plus q squared b il, etc. What is this thing called? This particular expansion? This particular expansion has a name. This is called the threshold expansion. Threshold expansion. Why is it called a threshold expansion? Because it starts only at the physical threshold. That's why it's called the threshold expansion. And why should it have this q to the power of 2l? This is the centrifugal barrier, okay? That is why it has this factor q to the power of 2l. You see, all these things look like mathematics. We are just doing some black magic writing expressions. No. Every one of these things has an obvious physical origin. So this thing here is a centrifugal barrier over here. And you can immediately see for small values of q squared, for small values of q squared, which is near the threshold, this thing is dominated by the lowest partial waves. It's only L equals 0 and L equals 1, which are going to play an important role at near the threshold, you see. So what is L equals 0 called? L equals 0 is called some wave, has a name. S wave, S wave. L equals 1, L equals 1, P wave, P wave. As L equals 2, it's called the D wave, etc. But you see, this thing, I want you to, now you have to really answer this question. Now tell me, looking at the symmetry properties of this thing here is symmetric under the interchange of T and U. This is the only guy who is antisymmetric under the interchange of T and U, okay? This thing again is symmetric under the interchange of T and U. However, our cosine theta here is T minus U by S minus 4m squared. This is antisymmetric under the interchange of T minus U, okay? So now, please predict for me, what are all the waves you will have for T0 and T2, and what are the waves you'll have for T1 based on this simple symmetry argument. And this, in this context, is what is known as generalized Bose statistics, okay? When people say generalized Bose statistics, sounds very impressive, but this is all it is. It has to do with the fact this is the only one that is antisymmetric under the interchange of T and U, while these two are symmetric. And you have to keep in mind that cosine theta, by the way, these are all very definite relations for equal mass scattering. When masses are unequal, all these expressions are much, much more complicated, okay? So one of the reasons why pi-pi scattering is so nice for theoreticians is it has all these beautiful symmetries and things just become much nicer. Okay, so someone predict for me, what are the waves that are present in this amplitude? What are the waves present in these two amplitudes? Okay. So this will have L equals 1, 3, 5, dot, dot, dot. equals 0, 2, 4. So that brings me back to my example over here, and then we have to see how the pi scattering amplitude plays a role in this particular form factor and how the I equals 1 p wave is entering into this unitarity relation. We don't care about all these things because it's only this guy which has the imaginary part. None of these things has any imaginary part. This is the only thing that has an imaginary part over here, okay? So that is what we have to do over here. Not only that, this has a slight complication that this is not in the S channel, but it's in the T channel, which means that one more piece of jugglery has to be done before you can establish that this thing here actually has the L equals 1 P wave sitting over here. Now, I can just finish that as the last piece that I can do over here for you all. So when you see this thing over here, where was it? T minus, where is it? Yeah. So let me go back to this. T minus u by 4m squared. No, by 4m squared, by f pi squared. I want to multiply and divide this by s minus 4m squared, s squared divided by f pi squared, like so. What shall I identify this with? What shall I identify this with? Cos theta. But I don't want to write it as cos theta, but I want to write it as P1 of cos theta. S minus 4m squared by 4 f pi squared. Okay? So this is the partial wave amplitude now. This is the partial wave amplitude. This is the pi, I equals 1, L equals 1, partial wave amplitude is just this, because the rest of it has got absorbed into the Legendre polynomial. Okay. So this guy over here, this q squared minus 4m squared, is f11 of whatever it is, t in this case. Okay. So let me check now that this is in fact correct. Now you can check, you can see that this 96 pi squared, f pi squared, all these things are correct, and then this satisfies the unitarity relation that was present on the blackboard some time ago, which I think has now been duly erased. What was that relation which was erased? Does anybody remember what that was? That the imaginary part of f goes as T11 of T times f. You can check that here by looking at this, looking at the imaginary part of this guy, so on. Okay. The imaginary part here is generated by this integral where there's a logarithm, and then it's also a funny logarithm because it has a square root object before that. Okay. So there's a problem with the branch over there also coming from the square root. Okay, so these are some of the things that I wanted to introduce you to. T11 is that partial wave amplitude, this one over here, this guy, this one. So this is my introduction to some of these ideas that I wanted to do using examples, okay? And we must develop a certain, facility with doing some of these calculations. Otherwise, it's not, okay, you can think about it and so on, but you have to just do these calculations, and things are made much easier if you can work out some of these things on Mathematica or even paper and pencil. So I wanted to stop here, see if there are any questions. There's a discussion session immediately now. 4:30, okay. Is it okay for me to stop now?